Hi everyone, I'm Prasoon. I'm a fourth year PhD student at UT Austin, advised by Professor Neeraj Yadwadkar in the UT SysML lab. And I'm here today to present our work in building a serverless platform that makes intelligent network bandwidth allocation decisions for serverless applications. So the cloud is great. Before the cloud, for developers to run applications or host web services, they would need to spend lots of money to buy their own hardware. Now, with the advent of cloud computing, the cost of running applications has greatly reduced. Developers now can pay much less by simply registering their applications on cloud platforms and leveraging the hardware offered by the cloud providers. So this is great. However, users still have to manage resource allocation, the amount of CPU cores, the amount of memory, and scaling as more requests to their application comes in. And so this increases the burden for developers and makes it challenging for everyday users to leverage the cloud. Hence, serverless computing was born. The goal of serverless is to make the cloud accessible to everyday users. With serverless, developers only need to submit their application, say a video processing function, to the serverless platform like AWS Lambda. Then, whenever a user submits an input to the application, AWS Lambda will determine the amount of resources to allocate the application. As more requests come in, Lambda will automatically scale the resources to the application on behalf of the developer. So this, creates a very friendly user experience now for users of the cloud. So how did serverless computing achieve this friendly user experience? Well, a key feature of serverless is that platforms automate resource allocations. To do this, commercial providers initially launched serverless platforms using simple allocation policies. For example, AWS Lambda, Google Cloud Functions, and then several other serverless platforms that followed used a coupled allocation policy where the amount of CPU cores allocated to a application is proportional to the amount of memory allocated. However, since the advent of serverless computing, several works have studied it and showed the inefficiencies of this coupled allocation policy, and thus instead make independent allocation decisions for CPU cores and memory to right-size the allocations for serverless functions. However, all of these works have ignored making intelligent network bandwidth allocation decisions, and in our work, we find that network bandwidth plays a crucial role in meeting the user requirements and maximizing the throughput of the serverless platform. For example, for six functions, we observe the variation in execution time as we vary the network bandwidth allocation from 16 to 1024 megabits per second. And we find that functions can exhibit up to a 10x variation in performance depending on the network bandwidth allocation. Therefore, it's essential to make intelligent allocation decisions to ensure that the end-to-end execution time of serverless applications meets the performance requirements that users might have. Now, one option to make allocation decisions is to continue following what AWS Lambda does and simply couple the amount of network bandwidth allocation and with the memory allocation. So we observe and study the impact of such a policy in our work, and what we find is that allocating more memory drastically reduces the network time shown in red here, and hence the overall execution time, since the amount of network bandwidth allocated increases proportionally to the memory allocation. So when given small memory allocations like 64 megabytes for image processing on the left here, it takes roughly 30 seconds to download the image, since it's only allocated 8 megabits per second of network bandwidth. Now, this download time alone violates the SLO for this function, which is around 7 to 8 seconds, shown by the dashed black line. Hence, to meet the SLO for this function, we would actually need to allocate the function over 512 megabytes of memory under a coupled allocation policy. However, this results in severe memory underutilization because these functions don't require such vast amount of memory. And we see similar trends across other serverless functions like mobile net inference on the right here. So ultimately, it's inefficient to make coupled resource allocation decisions for network bandwidth. This leads us to our objective, which is to make a serverless platform with a resource management framework that makes independent allocation decisions for each resource type, network bandwidth, CPU, and memory. Since there's been so much work already done with CPU and memory, we're going to focus on network bandwidth in this work. Now, before building out a system and any policies, we performed an extensive characterization study to understand what factors and how those factors influence the network bandwidth allocation decisions that we should be making. Due to time constraints, we're going to just present the three takeaways here, but we encourage you to check out our paper to view the data of our characterization. Now, we find that the network bandwidth allocation depends on three things. First is the compute time and the function semantics. So, for example, the thread level parallelism of the application. Second is the inputs given to the application at invocation time. And then third is specifically the size of those inputs, not really other properties, just the input size given to the application. So we use these takeaways to create an analytical model that enables us to estimate the required bandwidth to meet a function's SLO. The main idea of our model is to use the input size and break down the end-to-end latency of serverless functions to estimate the required network bandwidth. And so what we're going to do is go through the intuition that ultimately led us to our final analytical model. So the end-to-end latency of a serverless invocation with a given input I, like an image, for example, can be broken down into two parts, the network time and the compute time. Now, for the invocation to meet its SLO, the end-to-end latency needs to be less than the SLO. And we multiply this SLO by alpha, a value between 0 and 1, just to provide some slack. So if we substitute this into equation 1 and then rearrange some terms, we can compute the network time required to meet the SLO. Now, we also know the network time equals the input's size divided by the amount of network bandwidth allocated. So if we substitute equation 4 into equation 3, rearrange some terms, we can actually determine the required amount of network bandwidth required to meet the SLO for the input given its size and compute time. So in this final analytical model in orange, there are two unknowns, the size of the input and the compute time for the given input. Now we can retrieve the input size upon invocation time by analyzing its properties. However, estimating the compute time before runtime actually requires understanding the effects of the inputs and the amount of cores allocated to the invocation on the compute time. Hence, we use online linear regression to predict the compute time for each incoming invocation given its input. For brevity, we're going to kind of skip over the details of our formulation of this online learning agent, but please check out our paper for more details. With this algorithm, we built a serverless platform, SoloTune, which is a system that makes independent resource allocations per resource type and input-aware resource allocations. For every invocation sent to SoloTune in step 1, its resource allocator uses online learning in step 2 to predict the amount of cores, the amount of bandwidth, and memory required to meet the SLO. The invocation is then launched with this prediction in step 3, where SoloTune's daemon in step 4 observes the utilization and performance metrics like the execution time of the invocation and then sends this data back to the SoloTune's resource allocator for the resource allocator to update its agents online after the invocation completes in step 5. Now, this feedback loop repeats, ensuring SoloTune makes accurate predictions over time. For the sake of time, we're only going to present our end-to-end evaluation of SoloTune, but we encourage you to check out our paper where we have a lot more evaluation. So we observe the SLO violations as load or the request per second to the platform increases for SoloTune compared to two state-of-the-art baselines, Parrotfish and Bilal. Parrotfish couples network bandwidth with memory allocations, whereas Bilal does not limit bandwidth and instead defers all bandwidth decisions to the host OS like Linux. It simply provides the optimal CPU and memory allocation. Now, what we observe is that as load increases, SLO violations is increasing for all the systems. However, SoloTune, by simply making intelligent network bandwidth allocations, reduces SLO violations across loads. For example, at high load, it reduces violations by 1.3x compared to the baselines. Now, we also view the individual SLO violations for each function at high load, just to ensure that, SoloTune and show you that SoloTune is reducing SLO violations across functions, not necessarily for just one particular function. Hence, these preliminary results show that intelligent allocations for network bandwidth per function can greatly reduce the SLO violations as load increases and ultimately increase the throughput and the load that serverless systems can support. So, in summary, SoloTune, in this work, we show that the performance of serverless systems greatly depend on the amount of network bandwidth allocated to the functions, and that ignoring network bandwidth allocation decisions or making coupled allocation decisions is inefficient. Therefore, with our characterization study and our takeaways, we built SoloTune, an input-aware and an independent resource allocation framework that makes these, intelligent network bandwidth allocations per function. It uses analytical models to estimate the network bandwidth, the online learning to predict the compute time for a given invocation with an input, and then reduce it, and in doing so, reduces SLO violations by 1.3x compared to state-of-the-art baselines. We encourage you to check out our paper, and thank you for listening.